Welcome everyone. Thank you for coming to this talk. We are going to talk about 6LoWPAN networks, and more precisely how to do penetration testing on that type of networks. As you are going to understand, the hard part is not to do the actual penetration tests, but to reach to the point where you are able to do the tests. So a little bit of context. We are both security auditors from Airbus Defence and Space. We are working internally to do security audit and penetration testing within the Airbus group, but we also work with other companies to help them improve their security. So there's a picture of the one particular audit that will be the actual subject of this talk. That was water monitoring systems, and we did penetration testing on it. We are going to present to you the methodology, the tool we developed to do the test. We actually also are releasing the tool here, and we are also going to give you the results of this penetration test. So this network was relying on the 6LoWPAN protocol. So what is the 6LoWPAN protocol? Basically, it is IPv6 stretch and compress and torn apart in order to make it fit over the air, to have a lesser network footprint. Think here we are talking about smart grid. That means we want to have low energy infrastructure, low energy protocol. IPv6 is anything but low energy. Just one address is 128 bytes. You have two addresses, a source address and a destination address. This is a lot of information compared to the information that will be broadcasted by metering infrastructure. Think sensor that broadcast their information. So how the 6LoWPAN network actually do the compressing? That's quite simple. There's a 6LoWPAN header on top of the IPv6 header, with a lot of flags, and these flags just basically tell you how to decompress the IPv6 header. For example, you have a flag to say that the first 64 bytes of the IP address is the bytes from the MAC address. In fact, it's the IID address, but that's the equivalent, that's the MAC address. And so on. You have plenty of flags. You have flags, for example, for the TTL with predefined value. You cannot set the TTL precisely. You only have a few predefined value to choose from. You can also use flag to say that you are omitting a complete field because you do not need that field. You can also use context. Context are pre-shared information, and you have indexes. And so you just provide the index of the pre-shared information, and the device will just fill the blanks with this pre-shared information. Usually, it's in the context of metering infrastructure, you are broadcasting information, and if you miss one information, that's not critical. You have more information coming constantly. So you don't need to be sure that you get all the information, so you don't need a connected protocol, meaning you don't need TCP. So usually we find UDP on top of 6LoWPAN. That's why the 6LoWPAN standard also specify how to compress the UDP header, pretty much like it does with the IPv6 header. Keep in mind also that you have a short maximum transmission unit, only 127 bytes compared to the 1,500 bytes. So the 6LoWPAN protocol also specifies how to fragment and defragment IPv6 packets to 6LoWPAN packets. So what's the big deal? You know IPv6 is it's an IP protocol. There are already a lot of tools to interact with IPv6. Usually when you do penetration testing, you do not directly target the IP stack. You more Usually you're more about targeting the higher layer protocol, TCP, HTTP. So again, there's nothing new here. You can just use the existing tool, the existing methodology. So why not just use an USB adapter, just like you would do with Wi-Fi? Just buy a 6LoWPAN USB adapter, plug into your computer, and start doing the penetration test. Well, that would be too easy. The underlayer, under the 6LoWPAN protocol, so I mean the physical layer and the MAC sublayer, is handled by the 15.4 protocol. And this is where things get complicated. You have really a lot of possible configuration with 15.4. For example, you can set up the network topology as a mesh network, when every end device can communicate with each other, or as a star network, where end device must only send information to coordinators. But how to send this information? Well, you have also two types of transmission. You have the direct transmission, when one node will just send the information. You have the indirect transmission, when the node is going to first say that he has information pending and wait for the receiving node to say, okay, you can send the information. You can use GTSs, guaranteeing time slot. It's a system to allow time slot to each device to make sure that there's no collision. This is something that is optional. You do not need necessarily to use GTSs. And you can use beacons. Beacons in 6LoWPAN networks, I mean in 15.4 networks, not only are beaconing the network, but they also can host a lot of information if you want to. So you can see here that if you combine multiple choice, you can have really several possible configurations. But that's not all. You also have to think about security. Encryption, security, is provided by the MAC layer. And there again, you have multiple choices. You can only protect integrity, you can only protect confidentiality, or you can protect both. You can choose different type of key, I mean size of key, 32, 64, or 128. So again, more choice, so more possibilities if you make more combination with the previous possibilities I've exposed. And of course, you have multiple revision of the standard. You have the 2003 standard which specifies a type of encryption, which is incompatible with the encryption specified by the 2006 standard. And the 2006 standard is using the same encryption as the 2011, but the key management system is a little bit different. So, again, more combinations are possible. At that point, you should see that in order to connect, to use the IPv6 tool, so to connect to 6LoWPAN networks, you must first understand all precisely the configuration of the underlying 15.4 infrastructure. And this is really the hard part, because you have to guess, you have to brute force. If you're working with the customer that asks you to do the penetration test, you can ask for the information, but usually it does not have the information. It relies on the supplier to do the infrastructure. And if you ask the supplier, he might say that this is intellectual property, it does not want to share this information with you. You might want to directly get the information yourself by taking apart a sensor, for example. But if the sensor is embedded in a water pipe, that's quite difficult. Just to illustrate this, here are the list of possible encryption options on the 2003 standards. Here from the 2006, so you can see they are different. But one additional difficulty is that in the 2006 version of the frame format, you have 3 bits to specify the encryption you used. But that is not the case with the 2003 version of the standard. You have to know beforehand to guess the version of the choice you made for encryption. And of course, that is not all. Usually, when a supplier is building an infrastructure, 15.4 or something else, this supplier will be the one to build everything, the sensors, the coordinators, the border routers that connect the smart grid to the IT infrastructure. That means that if the supplier makes a mistake while implementing the norm, usually this mistake will stay unnoticed for long. By that I mean that if the mistake does not induce failure or performance losses, since every component in the network has this deviation from the standard, no one really will notice it for long. We have one good example of this. Well, actually, we have many, but this one, we can publicly talk about it because the component is publicly available to anyone. That is the XB S1 chip from DG, who is using the 2003 version of the frame format, but the 2006 security suites for encryption. This chips has been around since 2010, 2009, and nowhere on the internet we could find mention of this. And actually, we did get to talk with a DG engineer, and they realized this deviation by talking to us. So really, when I say that they can stay unnoticed and it's quite easy to encounter them when you're doing audit, that's really true. That is why we started the ARSEN project, that stands for Advanced Routing between 6LoWPAN and Ethernet networks. And the very idea of this project was to build two distinct tools. The first one was about a scanner that could detect every possible option from a 15.4 network, including deviations. And then from all this information would be provided to another tool, a border router, that would be able to translate IPv6 datagram to 6LoWPAN frames and vice versa, while using all the information provided by the scanner. This tool is based on another tool we've released 2 years ago, that is ZigBee Radio, which basically is ZigBee, a famous and very powerful packet manipulator, combined with GNU Radio, a software-defined radio framework that allows us to work with any kind of radio communication protocol. So, I said we have two main components in this project. The first one is very simple. I mean, it's the way it works. It simply builds a database of all devices that you can see by analyzing what ZigBee Radio is sniffing on the 15.4 network, and analyze this information to infer everything it can, actually. Which devices are running on which channel, which devices are communicating with each other, what type of frame they are communicating, what are the parameters, by that I mean also encryption parameters that are used to transmit these frames. On the other end, the 6LoWPAN border router, using this information from the scanner, create a tune interface. So it's not a tap interface, so actually we don't need Ethernet anymore. And basically it's a ZigBee automaton that will translate every datagram received on the tune interface into one or multiple 6LoWPAN frames, and translate while defragmenting any 6LoWPAN frames to an IPv6 frame and send it to the tune interface. We had to modify ZigBee Radio actually to achieve this. First, there were existing 15.4 layers and 6LoWPAN layers. As for the 15.4 layers, we fixed several bugs, but we also implemented both 2003 and 2006 version encryption methods. And we'll see later, we also implemented encryption not based on an encryption key, but based on key stream provided by the user. This is related to a cryptographic attack that Arnaud is going to present in a few slides. As for the 6LoWPAN, basically we implemented everything, mostly everything from the norm. It's almost rewriting from scratch. As far as we know from our tests, everything is implemented except from the indexes. Like I said, it's possible to work with context, The 6LoWPAN frame will provide indexes to know which context to pull out when the end device receives the frame. There's no way to know this context over the air, so this is not something we have implemented so far, but apart from that, everything else has been implemented.
So now let's talk about security attacks. So we will not focus on attacks on availability, because since we are talking about wireless, you can simply use a jammer and do a denial of service. So there is no big point to find another way to attack availability, because it's a simple route. We will mostly focus on confidentiality and integrity. And since we are talking about sensor for water management, for example, the critical point is integrity, because in fact confidentiality is not that much important at this level. But still. So for confidentiality, we'll talk about sameness attacks, and for integrity, we'll talk about replay attacks and malleability attack. So a few words on IES and CTR mode. So as Jonathan showed you, it's one of the modes used for encryption, and the most interesting one, we think. And what I will say is also true for CCM, so encryption and authentication. So why CTR mode? It's because if we use IES in CBC mode, it will do a block encryption, and since we are using short packets, I mean shorter than the size of the IRS block output, we will have to do a lot of padding, and transmitting padding over the air is the waste of efficiency and energy. So we use stream encryption, which is CTR mode. So one main point of stream encryption is we are using the key stream, which is the output of the block ciphering, and we XOR it with the plain text to have the ciphertext. One main concern with that, if we have several packets with the same key stream, we can do some crypto analysis. So each packet should have a different nonce, a different key stream, and if we see, it's meant to a different nonce. Since the counter is a RS counter, so it's predictable, and the key is of course constant. So the nonce is a value that will change between packets and avoid the possibility to do some crypto analysis with a lot of packets with the same key stream. So now the nonce on 15.4 is based on the source X ID, so it's something we can find, and frame counter. So in order to do our attack, we will need the same nonce attacks. So basically having a large number of frames with the same key stream, and so the same nonce, that will allow us to do our crypto analysis. So the replay attack is something really basic. You resend the packet that you have recorded, but you need to send it with the good counter value, because you have a frame counter. And the malleability attack is basically the two precedent together. So we need to know a key stream to craft our packet, and we need to know the value of the frame counter. Okay. So now time to do some pen test. So we know how security works. We have the tools that Jonathan introduced, and we have some guess on how we can attack it. So this is a wireless network used in water distribution. So we are working on it. And obviously, the first step of the pen test is like an IT pen test. We try to find as much information as possible. So we scan all channels of 15.4, and we find that there is communication on channel 18, that each sensor is communicate only with the PAN coordinator, which makes sense because if we have sensors, they are only broadcasting information. So it's a star topology, and the PAN is only transmitting beacon frame. So we can also see on the screen, it's a capture of the tools on the right side. We can see that the frame version is a 2006 standard, and security is used in CTR mode. And we have also the short address of the PAN and the sensor. But we will need the long address. As we have seen, it's used for the nodes. So we need the long address. So we know that the long address is, the extended or long address, the same, is transmitting when the sensor is associating with the pan. So basically, we need to force a new association. This is something you can find on a lot of attacks on wireless network. So how to do that? So we try to flout the sensor, so send a lot of frame and random frame to the sensor. So the sensor cannot track the pan, the beacon frame from the pan because the channel is full. And since the sensor is not receiving anymore any beacon frame, it will lose its synchronization. And if we stop flooding, it will resynchronize and so send its extended address. So we got it. The next step, and the simplest one, we want to add our fake sensor to the network. So basically, there is no secure function during the association process. We do not find any higher layer authentication system, and there is no filter on the address. We can use an address as we want. So it's basically straightforward. But we are able to connect our sensor, but we are not able to send frame because we cannot encrypt frame. We do not know the key. So as we see previously, our main goal is to manage this frame counter, so to predict its value. So the simplest way is to reset it, so we know it's 0. So we have some thinking about that. How can we reset this frame counter? And maybe its value is never stored in the non-volatile memory. So if we reboot the sensor, it resets to 0. So we want to reboot the sensor remotely. Obviously, we don't want to go and check the button. We want to do it remotely. So what we did is we flew the pan on each channel. So again, we broadcast a lot of frame. And the sensor will start looking up for a new pan, a new coordinator on every channel. And if they do not find any pan after a time, they will reboot. So we know how to reboot the sensor. So now we have to reboot the coordinator. So we use something the same way. We float the pan, so the sensor cannot connect to the pan because we are flooding the channel, only one channel. And we use a fake pan, so basically our tools set up on another channel. And we wait the sensor to connect, so we have to spoof the pan address, but we know it, so there is no challenge. And when the pan do not receive any answer for the sensor, the pan reboot. So now we know how to reboot the pan coordinator, we know how to reboot the sensor, we know that when we say reboot, the frame counter is reset. So what we do is we can get encrypted packet with the same nodes. We reboot the sensor, we record frame, so we know that the frame counter is starting to 0. We do that again and again and again, and we will need a lot of data, but it's wireless, so we have plenty of time to record, reset, record, and after that we do some crypto analysis and to guess the plain text. Obviously, if you have some inside of the plain text, it's easier. For example, if we know that we are talking about sensor, water sensor, we can think that the value will not change really fast. And it's the kind of thing that can help on the crystal analysis. So we are also able to do replay attacks. Since we can manage the frame counter, we can replay a packet with the same counter value. So we start attacking integrity, and it's quite interesting. But of course, what we want is crafting and injecting our frame. But we have, in fact, everything we need, because from the same nonce attack, we know the plain text. And if we know the plain text and the ciphertext, of course, we can have the case stream. And with the case stream and the value, and knowing the value of the counter, again, we can reset it. We can craft our packet, our encrypted packet, and send it with our fake sensor. And so we can send any value we want on the pan, and integrity is not anymore. Maybe.
So, as Arnaud just showed you, we started from scratch. We had no information because, like I said previously, the sensors were buried in Python, and we could not have any information, at least the way we worked. And we ended up being able to craft encrypted packet. So that means that we had all we needed to feed to our border router to be able to route IPv6 frame from 6LoWPAN frames, and thus we were at home. We could use Nmap, we can use whatever we wanted. So we're not talking about the rest because this is nothing new actually, doing Nmap and stuff. But really the hard part is to get from the we know nothing about the network to we are able to craft to forward IPv6 packets to the 6LoWPAN networks. The reason we were able to do so is because the supplier did 4 big mistakes that are very common. First, let me say that the usual way to work on that encryption aspect is to find a JTAG, a BDM, or something to extract the firmware, and from that firmware to extract the key. But since we were not able to do that, we had to work at the encryption level. So the mistakes made by the supplier was first to think that encryption protects integrity. If you do not have the key, you cannot forge packet. That is not true. Integrity code, MIC or MAC, are there to protect integrity. Encryption only protects confidentiality. And actually, in a sensor network, confidentiality is not that important. Integrity and availability are the 2 aspects that are very important. One of the mistakes was sorry, let me get that. I was sure to have them in the right order. Okay. Non-volatile memory. Usually when you have counters to prevent replay attacks, these counters are only kept in memory and they are never stored in non-volatile memory. That means that if you are able to reboot a device, you reset the counters and you have replay attacks. And if you have not used cryptography properly, you have both replay attacks and semblance attack, and then you can have malleability attack and thus forge encrypted frame without having the key. And rebooting devices actually are not that hard because with sensor network, the main consideration is always availability. And rebooting is always the last resort when they don't understand why the coordinator does not receive any information, why the sensors are not able to synchronize with the coordinator. Whenever something won't happen, they try many things, but at some point, the last resort is always to reboot. So if you play with the network, at some point, you will force a reboot, and you will force a lot of things like association procedure, like resetting of the counters, and so on. So obviously we didn't break the water pipes with us, but we have a little demonstration here. So sorry, what? Oh, so remember, I said that the deviation are possible. So we set up Arduinos, simple Arduinos, with the ZigBee chip I told earlier that is not compliant with the standard. And we set up the Arsene tool with the Skype radio and the USRP to do the SDR part. And if you switch to the next slide, you can see that I can do actually this with my computer right now. I don't know if I can plug the VGA cable. Too far. Okay. Yeah. I have to move all that. Okay. Let's say if you have questions, don't hesitate to come here, and we will show you the demonstration. But basically, if you can see, I do ping, I do Nmap, I do telnet, and I'll do all this for my computer. That computer has no idea he's talking to 6LoWPAN networks. The border router, with all the information provided by the scanner, is doing the job. So I can pretty much do standard penetration testing on these components without having to take care of the 6LoWPAN and the 15.4 parts of the network. And that's it for the presentation. I thank you. If you have any questions.
And if you want to see the demo closer, please come. We have some time, I think, so you can see it.